we are going to talk about tree diagrams. Now, let me illustrate the idea of tree diagram with this example, right? We have two boxes. In box A, we have 3 red, 1 blue, and 2 green balls, alright? In box B, we have 4 red and 2 blues. And we pick one ball from each box and want to see what is the probability for each, different possibilities. So we have to divide the event into 2 stages. In stage 1, we pick the ball from box A, alright? Now, the picking from box A, there are 3 possibilities. Either it is a red, or it is a green, or it is a blue, alright? 3 different possibilities. We can assign probability on each branch, alright? To pick a red ball from box A, the probability will be 3 out of 6, alright? To pick a green, it is 2 out of 6. To pick a blue, it is 1 out of 6, alright? These are the probabilities, picking different colors from box A. And then, regardless of the first draw, right, that would be the red one here, the green one, and the blue one. But regardless of the first draw, in the second draw from box B, we will always have 2 possibilities. It's either a red or a blue coming out from box B. Alright, so in each of these branch, we can assign the probability. To have a red, it is 4 over 6, the probability. To have a blue, it is 2 out of 6, alright, because of the number of balls in box B, alright. Anyway, so we can duplicate these branches and, apply to the other events, alright. So it will be like this. The red branch will be 4 out of 6, and the blue branch will be 2 out of 6, alright. So at the end, we have all these events now, alright. So we can summarize all the events on the right hand side, right? So the first one, what does that mean? That means we have a red ball from A and a red ball from B, alright? And we can have indicate the events like this, right? And then we have a green, and then we can have the blue, alright? Okay, so here are all the possibilities, alright? So this endpoint means that, for example, we draw the blue ball from A, and then we draw the red ball from B, alright? Alright, so that is for each individual event. So how likely is each event? We know that to draw 2 blue is not the same probability of having draw 2 red, right? Because there is not much blue, but there are many reds, alright? It is more likely to draw the red, alright? It is less likely to draw 2 blues, right? But how do you compare the probability in terms of numbers, right? In terms of quantitative analysis? So we can do this. The probability for each event is the product of all the probabilities that leads to that event, alright? The probability for each of these endpoints is the probability for all the branches that leads to that endpoint, alright? For example, red, right? First, it transfers this branch, and then it goes through this branch. So the probability for the first event is 3 out of 6 times 4 out of 6. 3 out of 6 times 4 out of 6. And the answer goes to 12 out of 36. Alright? By similar token, say this event, right? What is the probability? The probability will be this blue branch and then this red branch. Alright? That will be the product of all the branches that leads to that event. So that is 1 over 6 times 4 over 6. And the probability for that event is 4 out of 36. Alright? So let me quickly calculate the other events for comparison. It is 8 out of 36, right? This is 4 out of 36. And the last one is 2 out of 36, alright? Am I right? So these are the probability for all these events. Alright, I did not do all the calculation. You can fill in the calculation in between on your own, alright? Just to check that I'm correct. So that is the tree diagram, right? It describes every possible event in this endeavor, and you calculate the probability for each corresponding event. Alright, so if I want to know, well, how likely is that we get a green from A, and then we get the blue from B, how likely is that? Oh, we can consult the tree diagram and immediately you know the answer. Alright, the green from A, the blue from B will be 4 out of 36, and that is 1/9. Alright, so this is it. Now, but this tree diagram illustrates two important principles in the construction of the tree diagram. Alright, so we have principle number 1, that all the probabilities coming out from the same branch, from the same node, all the branches, the probability should add up equals to 1. Alright, if it is not 1, then perhaps you missed something. Alright, you see all these three probabilities coming out from the same point. Alright, their sum should be 1. Am I right? 3 out of 6, 2 out of 6, 1/6 add up to 1. Alright, and for example, the same node here, you have two possibilities, two branches coming out from the same node, from the same point. Alright, and their sum 4/6 plus 2/6 is 1. Alright, and it applies to the endpoint as well. If you look at all these endpoints, alright, you try to add them up together, the sum equals to 1. Am I right? 12 plus 6 plus 8 plus 4 plus 4 plus 2 is 36. Right? Now, that's why I keep them the same denominator for easier addition. Alright, if I simplify the fractions too early, then that would be quite difficult to add them up all these fractions. It's a nightmare to add up all these fractions, isn't it? So I do not simplify. I try to keep it in the same denominator until the very end. Right? The answers, however, must be presented as a simplified fraction. But the intermediate calculation, I would rather keep it to the same denominator. Alright. You can check the integrity of the tree diagram by noting that the sum of all the probabilities coming out from the same node, all the branches should add up to 1. If it is smaller than 1, perhaps you missed something. Right? If you miss the blue branch entirely, then you discover that this is not a complete tree diagram because these probabilities do not add up to 1. Alright, so there's a quick check to see whether you make the complete, whether you exhaust all the possibilities. Right? That is the first principle in doing the tree diagram. And the second principle is the one I just talked about. Alright, the probability for each endpoint is the product of all the probabilities that leads to that event. Alright, there are some other branches, but I don't care. I don't care about the other branches. Alright, the probability of this event will be the red number times the green number times the blue number. Alright, if from the start to the end it goes through the red tree, the green tree, and the red branch, the green branch, and the blue branch. Alright, the probability for this endpoint will be the product, the multiplication of all the branches that leads to the final event. Alright, this is the second principle in the construction of the tree diagram. Alright, when you make the tree diagram, make sure you follow this construction. Alright, number 1, all the branches coming out from the same node, the probability, the sum must be 1. Alright, and then the same principle applies to on the far right. Alright, if you add up the probability of all the final events, they should equal to 1. Secondly, is the endpoint probability is the product of all the branches multiplied together that leads to that event. Okay, so let's look at another example. So once again, we have two boxes, right? We have a red, blue, green in A, and same red, blue, green in B, but they have different quantities. Now we pick a ball from each box. Alright, one ball from box A, one ball from box B. What is the probability that the two balls having the same color? Right? So let's construct the tree diagram. Once again, there are two stages. Right? We have the one stage from box A. There are three different colors coming out from box A. It can be red, it can be blue, it can be green. Alright, and then we can assign the probability. To have a red, it is 2 over 6. To have blue is 2 over 6. To have 2 over 5, I'm sorry. It is now 5, right? The previous example was 6, but here there are only 5, alright? And there's 1 over 5 for the green, alright? And then in stage 2, we have once again 3 different colors coming out from box B, but their relative probability is different. Alright, we have 1/5 for the red, 1/5 for the blue, and then 3/5 for the green. It's a 3. Alright, so we can repeat this part and copy to the other colors. I hope there is enough space to copy the other colors. Alright, so let me adjust this one a little bit. Alright, this is a bigger tree diagram compared to the previous one. Alright, so this is it. Alright, the blue one is 2/5, the green one is 1/5. Alright, so now we have all these endpoints. We have 9 different possibilities. Alright, and they correspond to red and red, and then 3 blues, and then the greens from A. Alright, now this column, they are the color of the balls coming from box A. Alright, and then coming from box B, we have some different colors as well. Alright, we have the blue, and then we have the green. Alright, so these are all the possibilities. We can calculate the probability for each event, right? The first one, red and red, will be the product of these 2 branches, right? The probability of each endpoint is the product of all the branches that leads to that event, alright? So this one will be 2/25, alright? And then the reds will be like this. There's a 2, there's a 6, that is a 2 and a 2 and a 6, and a 1 and a 1 and a 3. Alright, to check for the integrity of the tree diagram, we can add up all these endpoints, and if I am correct, then they should add up to 1. Alright, these are all out of 25. That's why I keep them in the same denominator. I will do the simplification last, but well, we don't have any simplification here, but never mind. Alright, even if there were simplification, I will keep it at the last step. I will try to keep them as the same denominator for easier comparison. Alright, so there's a 10, there's a 10, 20, 25. Alright, so all these probabilities add up to 1. Alright, they should sum up to 1. Their sum equals to 1. Alright. Alright, so that is the entire possibility, what we call the probability space. Alright, that is what we call the probability space. All the possibilities and how likely is each possibility. Alright, it's a complete description of the situation. Now all we need to do now is to cherry pick the answer. Alright, cherry picking means we choose the one that we want. Alright, now we want to have the probability having the same color, so we cherry pick this one, the event, this event, and this event. Right? We pick up the red, red, blue, blue, and the green, green event and add them up together. Alright, so the answer will be 2 and 2 and 3 divided by 25, and the answer goes to 7/25. Alright, this is the answer, the probability of having the same color. Because having the same color, there are 3 ways. You can have red and red, you can have blue and blue, you can have green and green. That's all. Alright, the others, they are different color. So red and red, blue and blue, green and green, the color, the probabilities, they are like this respectively. Alright, so the final answer is 7/25. Alright, so that's how we do it in the probability. Say if we have for example, if I want to ask what is the probability of having at least 1 red, right? What is the probability of having at least 1 red? Then you just refer to the same tree diagram and cherry pick the results you want. Alright, at least 1 red means this one is at least 1 red, so it's this one, this one, this one, and this one. Am I right? In the purple column, I am cherry picking the answer that I like, that meets the description, at least 1 red, right? So the answer goes to 2 and 2 and 6 and 2 and 1. Alright, all together divide by 25, so that is 13 divided by 25. This is the answer. if you want to have the probability of at least one red. Alright. In fact, if you are good at it, you don't have to draw the complete diagram. You just consider what are the relative branches. Alright, so you don't really have to draw the tree diagram. Say the probability having the same color, right? You can think about that. That would be just red, red, and blue, blue, and green, green. Alright, you don't have to waste time to consider those that are not in consideration. Alright, you can just think about this. Alright, the probability will be like this. So the first one to be red, the probability is 2/5. The second one to be red will be 1/5. Alright, and then so on for the others. First one green is 1/5. The second one green is 3/5. Alright, so you can add up all these probabilities and come up to the orange answer. Alright, this is the probability of having the same color. You can just do this without referring to the whole tree diagram. Alright, but if you have the same tree diagram, you can refer to not just the orange question. You can even answer the purple question, right? What is the probability of having at least one red? And what is probably having not more than one green, something like that, right? You can answer whatever question they have referring to the tree diagram. Or like below the dotted line, you can just consider the case that you want and you don't have to draw the complete tree diagram. Alright.